Assalamu alaikum. This is lecture number 7 of the Control Systems course. In the previous few lectures, you have understood and studied the concept of Laplace transform and the inverse Laplace transform. You have studied the partial fraction expansions and the solution of differential equations. Now we are ready to represent the system in a form where the input, the output, and the system can be represented separately. So in this course, generally we will deal with the time invariant system or linear time invariant systems, LTI systems. And the LTI systems can be represented by constant coefficient differential equations like this one. The constant coefficient means that these coefficients do not depend on time. They do not vary with time. So in this differential equation, C of t is the system output, R of t is the system input, and AI and BI are coefficients. So if we take Laplace transform of both sides and assume that all the initial conditions are 0, we are left with this equation. The same equation is written here again. We can see that by using the Laplace transform, now we can take out the C of s and the R of s. If we were using the differential equations form, we could not do that. Now if we shift the R of s on the left side and the term with the C of s onto the right side, we are left with this equation. This expression is called the transfer function of an LTI system. So by definition, the transfer function is the ratio of the output C of s divided by the input R of s, assuming all the initial condition equals to 0. We can also represent the transfer function into a block diagram form represented here, where the inputs are represented on the left side, the output is represented on the right side, and the transfer function itself, which is represented by G of s, is written inside the block. So from this representation, we can see that we can find the output of the system C of s by just multiplying the input R of s by G of s. So C of s will be equal to just R of s multiplied by G of s. From here we can see that now the input R of s, the output C of s, and the system itself are entirely separate. And also the transfer function G of s is written by or represented by two polynomials, and the highest power of denominator of G of s, which is n, this represents the order of the system. So let's go ahead and find the system response from the transfer function. So if we are given a system transfer function and we have to find the response of the system, we can easily find this. So in this problem, we have to find the stepped response of the system, which have the following transfer function. So what does that mean? It means that R of t in this case will be a step function, which is u of t. And if we represent this R of t into the Laplace domain, then we can represent it as R of s, which will be equal to 1 by s, because we know that the Laplace transform of u of t is 1 by s. And in the previous slide, we saw that C of s, which is the output of the system, this can be found by just multiplying this R of s by the transfer function G of s. So we will be left with 1 over s into s plus 2. So from the previous discussion of the partial fraction expansion, we can write this C of s as K1 divided by S plus K2 divided by S plus 2. And from simple manipulations, we can find that K1 is equal to 1 by 2 and K2 is equal to minus 1 by 2. Hence, the CFS will be now 1 by 2 divided by S and minus 1 by 2 divided by S. Actually, it is S plus 2. So we want to find the system response, and that is in frequency domain. So what we have to do is we have to apply the inverse Laplace transform. So if we apply the inverse Laplace transform on this equation, we will get C of t, and we already know that 1 by 2 will be as it is, and we know that the inverse Laplace transform of 1 by s is just 1, and similarly 1 by 2 will be as it is, and we know that 1 over s by 2 has the inverse Laplace transform as e raised to power minus 2t, and we can write a u of t as well. It just shows that this is a causal system, and c of t is beyond time equals to 0. So from this equation, we can see that this response, which will die out after some time, this response represents the transient response, and when all transients die out, then we are left with this response, which is the steady state response of the system. In the remaining of this lecture and the next few lectures, we will formally apply the transfer function to model different physical systems. So firstly, we will find the transfer function of electrical networks. You are familiar with the table which represents the voltage current, current voltage, and voltage charge relationship of different passive electric components like capacitor, resistor, and inductor. So the first method to model the electrical network is to find the differential equation which describes the dynamics of a electrical network, and then apply the Laplace transform to the differential equation, and from there find the transfer function for the electrical network. There is another much simpler way to find the transfer function of electrical networks by first transforming the electrical network into the Laplace domain. We can do this by first transforming these voltage equations into the Laplace domain. So for the capacitor, we can write the voltage equation as V of s equals to 1 over c, and we know that integration is transformed into just the multiplication of 1 by s. So we can write it as 1 over c s multiplied by the I of s. And similarly, for the resistor, we can write the voltage equation as V of s equals to just R into I of s. And if, in the case of inductor, we can write the voltage equation into the Laplace domain as V of s equals to the L, and the differential can be represented as S into I of s. So in the current problem, we are given with a series RLC circuit, and we have to find its transfer function, where the input to the system is the applied voltage V of t, and the output to the system is the voltage across the capacitor. We have gone through this You have gone through this problem in the previous lecture, where you found the differential equation by using the KVL, and by applying the Laplace transform you found the transfer function. So this is the final transfer function you found by taking the Laplace transform of the differential equation. We can also find the transfer function by first transforming the same RLC series circuit into the Laplace transformed circuit, where we transform each component, which was previously in the time domain, into the Laplace domain, and also we transform each component and replace the value of the component by the equivalent impedance also found in that table. From here you can find VFS, which will be just I of S into C of S, where Z of S is the equivalent impedance, and equivalent impedance will be just addition of all of these impedances, as we can see here in this equation. And from here we can find the I of S by V of S, but as we want to find the transfer function between Vc and VFS, so we also know that Vc is related to the current by this equation. So from here we can find the I of S, which will be just Vc of S into C of S, and if we apply this I of S in this equation, from here we can see that Vc of S will be equal to, multiplied by C of S divided by V of S will be equal to 1 over Ls plus R plus 1 over C of S. And if we multiply this C of S on the right side, we can easily find the transfer function which I'm writing here. Is C of S divided by V of S, it will be equal to 1 over LC S square plus R CS plus C will be cancelled out and we will be left, CS will be cancelled out and we will be left with 1. And this is the same transfer function which we found earlier. And we can see that it involves only a few steps. So in the next few examples, we will first transform the circuit into the equivalent Laplace transformed circuit, and from there we can easily find the transfer function of the electrical circuit. To apply the previous procedure to model complex electrical circuits via firstly mesh analysis, we will firstly replace the passive elements with their impedances, and then we will replace all sources and their time variables with their Laplace transform. And if we have more than one mesh, then we will assume a current direction in each mesh, and after that we will write Kirchhoff's voltage law or KVL around each mesh. So when we have more than one mesh, we will be left with simultaneous equations for the output, and then we will solve these simultaneous equations by using Cramer's rule, and then after that we will find the transfer function. Let's go and solve a complex electrical circuit with more than one mesh. Here we have an electrical network with more than one mesh. So firstly what we will do, we will transform this time domain circuit into the equivalent Laplace transformed circuit, where we will replace the voltage and currents into their equivalent Laplace transformed versions, and also we will transform the component values to their equivalent Laplace transformed impedances. So now what we will do is we will write equation for each mesh. Like here, this is for the first mesh. So this equation is found by just applying the KVL on the first loop here. And when we are dealing with the first loop, we will take the sign of the I1 as positive and sign of I2 as negative. And similarly, when we apply the KVL in the second loop, we will take I2 as the sign of I2 as positive and sign of I1 as negative, as we did here. And we can see that here in the second loop there is no energy or voltage source. That's why the right hand side is 0. So in the current problem, the output is I2 and the input is V. So we will apply the Cramer's rule and we will find the I2 from these two simultaneous equations. And to apply the Cramer's rule, we will firstly separate the I2 and the I1 terms like we did here. And after that, we can easily find the I2. So in the Cramer's rule, we take the first column related to the I1 here and the right hand side, and we take the determinant of these two columns and divided by the determinant of the left side, which is written here. And after finding the determinant of the numerator, we are left with L of s and V of s, and from here we can find the transfer function I2 of s divided by V of s, which will be just L of s divided by the delta, and where the delta is the determinant written here. So after finding the determinant delta, we are left with the following transfer function given here. And now we can write this transfer function into the block diagram form, where the I2 of s is the output and V of s is the input to the system. So if we observe the simultaneous equation we found in the previous slide, we can see that the process can be summarized here. So this process says that sum of all the impedances around mesh 1 into I1 of s minus sum of impedances common to the two meshes into I2 of s will be equal to the sum of applied voltages around mesh 1. So this will give you the first simultaneous equation. So this is an observation-based shortcut method to find the simultaneous equation directly by looking at the circuit. Like I can write the equation directly by looking at this network as sum of impedances around mesh 1 are R1 plus L of s into I1 of s minus sum of impedances common to the two meshes is just L of s multiplied with I2 of s and equals to the sum of applied voltages around mesh 1, which is just V of s. And similarly, if we apply the second observation based method, we can find the second simultaneous equation for the loop 2. So it will be a minus sum of impedances common to the two meshes, which is just L of s multiplied with I1 of s, and plus sum of impedances around mesh 2, which are R2 plus 1 by Cs multiplied with I2 of s equals to sum of applied voltages around mesh 2, which are 0. So you can verify that these two simultaneous equations are exactly the same we found in the previous slide. So similarly, we can apply the methods we just studied to the electrical networks with more than one node, and we can also apply the nodal methods to find the transfer function as well. So far we have only discussed the mathematical modeling of electrical networks containing passive elements like resistors, capacitors, and inductors. We can also extend the discussion to include the active components like operational amplifiers. So the operational amplifiers are the electronic amplifiers. They are also used to implement the transfer functions. So ideal operational amplifiers has the following characteristics. They have the differential input, and they have ideally very high input impedance. We can say that input impedance is infinity, and ideally they have very low output impedance, so we can say Z naught equals to 0, and ideally they have a very high gain amplification, and the output is given by this expression where A is gain and V2 minus V1 is the difference between V2 and V1. So let's take an example of an inverting operational amplifier where the second input V2 is connected to the ground. So we can say that V2 is equal to 0 here. From the previous given expression, we can say that V0 now will be minus A V1, and this minus sign shows that the output will be inverted, hence the name inverting operational amplifier. So if we connect some impedances in this fashion as represented in this figure below, then we understand that input impedance is too high. So if the input impedance is too high, then this current IA of S will be approximately equal to 0. So if this is approximately equal to 0, then if this is the case, then I1 will be equal to minus I2 of S. And also we know that I1 of S is equal to VI over Z1 of S, and also minus I2 will be equal to minus V0 by Z2. So if we put I1 and I2 in this equation, we will get the relationship between output of the operational amplifier to its input Vi. So this is the transfer function of the inverting operational amplifier, which states that the transfer function of an operational amplifier is just Z2 divided by Z1, where Z2 is this impedance or resistance, and Z1 is this impedance or resistance. So let's solve a problem where we have to find the transfer function of an inverting operational amplifier circuit given here, and the transfer function is between the output of the operational amplifier and the input of the circuit. So now from the previous slide we know that the transfer function of the operational amplifier or the inverting operational amplifier is just minus Z2 by Z1. So this is Z2 and this is Z1. So firstly we will transform this circuit into the equivalent Laplace transform circuit, where the C1 will be now C1 into S, and R1 will be same, and R2 will be same, and C2 will be now C2 into S. Now the Z, this is Z2 and this is Z1. Z1 is in parallel and Z2 is in series. We can so we can easily find Z1 and Z2. Here we have found Z1 and here we have found Z2, and we know that the transfer function will be just minus Z2 divided by Z1, and if we put Z2 and Z1 here, we will get the following transfer function. So this concludes our discussion on the electrical networks. In the next lecture we will continue the discussion on the mathematical modeling of physical systems, and in the next lecture we will do the mathematical modeling of mechanical systems.